Hello. Today we are going to continue our discussion of size exclusion chromatography or gel permeation chromatography. Same thing. And what we are going to do is start by breaking down the volume of the solvent that passes through the column into two components, the interstitial volume and the volume that is interior to the pores, which comes out later. So just as a quick recap, remember that size exclusion chromatography separates polymer chains on the basis of the size of the polymer blobs as they go through. And those that are bigger go around the beads, and those that are smaller get temporarily trapped in the pores in the beads and have a much longer pathway through the column, and therefore have a longer retention time, and therefore larger particles, larger polymer blobs come through first, and smaller polymer blobs come through later. So let's think about the separation mechanism in a bit more detail. So SEC separation mechanism. Let's picture a narrow band of solvent entering the column. Entering the column. So we have the total volume of the solvent equals some V naught, which is the void volume, plus the interior volume inside the pores. So this is interstitial in voids between the beads. And this is the stagnant or slower moving solvent in the pores. So V naught goes through the column at the imposed flow rate from the pump in our system. And this we just set on the software. And of course, the larger chains come out first. The word that we use in the chromatography business is called elute. The larger chains elute first. And progressively smaller molecules have access to successively larger fractions of the internal volume. Progressively smaller fractions have access to successively larger fractions of the internal volume. The internal volume VI. And as the internal volume emerges, successive fractions of the polymer come with it. Okay, got this? You can pause it if not. So then we have a modified equation for the retention volume. So the retention volume for a particular molecular weight fraction retention volume equals the interstitial void volume plus some coefficient Kd that is specific to the pore size and the sizes of the polymers going through the system, and this is the distribution coefficient. And it is a function of the pore size and the molecular size. And it indicates what fraction of the internal volume is accessible to a particular solute. Internal volume V sub I is accessible to a particular solute. And the consequence, if Kd equals zero, then the solute is excluded from the pores. And the other limiting case is that if Kd equals 1, the solute totally penetrates the pores. Now ideally we want a Kd that's between 0 and 1 so that we get some retention but not complete retention. And we can model using a kind of a simple model what a Kd actually means from the standpoint of the polymer chains as they travel through the column. Using the following diagram for the significance of K. So imagine we have a cylindrical pore, and we have some polymer blobs with radius r. This could be something like the radius of gyration, r sub g, that we talked about last time. And The diameter of this cylindrical pore we will call A, and the length of the pore we'll call L. Now, as the solvent or as the solute molecule goes into the pore, the center of the solute can actually enter a cylinder that's actually smaller than the actual cylinder because it has some finite radius. So really it's this cylinder that the center of the solute has access to. So the sphere may only enter a cylinder enter a smaller cylinder with radius A minus R, which is this dotted cylinder. And thus the concentration inside the pore is always going to be less than the concentration outside the pore. And the amount that it's less inside the pore is going to depend on the size of the solute. For large solutes, the concentration in here is going to be vanishingly small, because as the smaller cylinder gets smaller, as R gets bigger, then the number of molecules that can make it in here per unit volume is going to be small. So concentration will get smaller inside the pores as the particle size gets bigger. So K is in actuality the fraction of the exterior concentration inside the pore. Inside the pore, not inside pore. And this equals the accessible volume over the actual volume. Divided by the actual volume. Or we have pi A minus R quantity squared times L over the actual volume is pi times A squared times L. So for spherical particles, and cylindrical pores, KD equals A minus R squared over A squared, or rearranged 1 minus R over A quantity squared. So in the two limiting cases, KD equals 0 for R equals A, and therefore the solute is excluded from the pores. And as the solvent or solute radius approaches 0, Kd equals 1, and that means that the entire interior of the pore is included. Now, what does that give us in terms of separation of our detector output? What we're going to do is plot log of the absolute molecular weight. This isn't an average molecular weight, it's the actual molecular weight of a specific fraction that comes out. So this is log of the molecular weight, and I want to plot these on the same axis, so we'll use one of these guys versus V sub r, the retention volume, which is related to the retention time by the flow rate. So we'll plot log of the molecular weight up here and the detector output down here. So what we have at first for large molecular weights is some regime in which the polymers are completely excluded from the pores. Then we have a region which is about 2 orders of magnitude in M, where we do achieve separation. And this is so this is about 2 orders of magnitude. Or 2 logs. And this is the useful range. And for some given fraction, the volume here is Kd VI, whereas this entire useful range is VI. And then over here, the solute is so small that it goes through all the pores. So this is the all pore regime. This is the some pore regime. And this is the no pores regime. So where we want to be is right here. And what does the detector output look like? Is something like this. And at any given time, or retention volume, which again are interconvertible by the imposed flow rate, VR for a given fraction equals V naught plus Kd VI. So what we do in order to calibrate the system then is to take a series of polymers with a known molecular weight. Often this is polystyrene. Then we run those through the system and we generate this plot. Then we take a system of unknown molecular weight and we run it through the system again, and we assume that if the hydrodynamic volume has the same dependence on molecular weight as for our standards, and if we chose our standards properly, this is a pretty good assumption, but there are caveats which we'll talk about. Then we can assume that the molecular weight of the unknown sample is the same as the molecular weight of the standard. Now this seems simple, right? It should work every time, but it doesn't, because polymers do not always have easily predicted size hydrodynamic volumes based only on molecular weights. So sometimes they could be different from our standards. So remember that the separation is based on the hydrodynamic volume, not the molecular weight. So hydrodynamic volume proportional to radius of gyration cubed, not the molecular weight. So look at different backbone rigidities. Let's imagine 4 different polymers with the same molecular weight. Let's take polyethylene, PS, sorry, polyethylene is PE, polystyrene is PS. Let's take an example from my research area, which is polyethylene, which is a semiconducting polymer. And then let's take a crazy polymer called a ladder polymer. And we're showing this just to show how crazy stiff a polymer chain can become. Sorry. This is a ladder polymer called BBL. And it's called a ladder polymer because it has rungs on a ladder, like you could climb this, because it really has 2 backbones along the entire molecular axis with rungs the entire way. So it's a very rigid polymer. And let's just kind of schematically think about how these things ball up once they're in solution. Now, polyethylene is the most flexible, so it might look roughly and scientifically like this. Polystyrene is a little bit more rigid, so it's going to relax a little bit more. And maybe the radius of gyration is, remember, from the center of mass, root mean squared distance from the center of mass to the average monomer. So maybe the radius of gyration is somewhere like this. Polyethylene is going to be even stiffer, so maybe it might kind of look like that. And then this ladder polymer, sometimes they don't even fold back on themselves, or if they do, maybe it's like a long, lazy turn like these. So we have different, which one is, even though they're all the same molecular weight, this one is going to come out way sooner because it has a larger hydrodynamic volume than this one. So we need to be very careful about which standards we use and interpret all of our data in light of these different standards. So there's some other limitations as well. One is that suppose there is some kind of specific chemical interaction with the matrix material. So suppose you have some matrix that forms a specific interaction with the polymer of interest and might slow it down compared to the standard. Or suppose that your polymer is branched, and branched polymers, size exclusion chromatography is particularly bad at dealing with. So highly branched polystyrene or polyethylene probably wouldn't respond well to determination by SEC. Okay, I'm going to tell you a little bit about the details of the detectors that we use, and we won't go into too much detail. I just want to show you where these signals come from. So this is downstream of the column. We'll have a detector, and the two most common are refractive index detectors. So we have refractive index, or RI, and it follows a law where the refractive index as a function of concentration equals the refractive index of the solvent plus dN dC, which is the rate of change of the refractive index as a function of concentration, which will be different depending on each analyte times the concentration. So this is the RI of the eluent. This is the RI of solvent. And then this is the rate of change of the refractive index with concentration. And this is something that we have to measure separately, times the polymer concentration. And this is going to be, the DNDC is going to be solvent dependent as well. So you have a beam of light that's going to be refracted by the solution in a proportion to the difference between the refractive index of the eluent and the refractive index of the solvent. So the light beam will be deflected by the eluent in amount proportional to n of C minus n of S, which will be proportional to the concentration once we determine what DNDC is. Okay, now this works with any material with any polymer that changes the refractive index, but sometimes it's useful to know if you have multiple materials in your column, if they absorb in the UV vis, you can luckily use a UV visible absorption detector as well. And this will allow you to resolve one type of polymer that absorbs at a different wavelength from another polymer that may also be present in the mixture that might absorb at a separate wavelength. So you can actually do like spectroscopy as the polymers come out. So UV vis and the absorbance of the solution is related to absorbance of the absorbing species. By Beer's law, which is epsilon BC equals the absorption equals the base 10 log of I naught over IT. Now what is all this stuff? This is the absorptivity, which is a function of wavelength. B is the path length. Sometimes epsilon absorptivity is called the extinction coefficient, which is a function of wavelength. Sometimes you'll get the whole, you can set this at a specific wavelength, or you might have a monochromator in your system that can actually give you a UV vis spectrum for every fraction of material that comes out of the column, which is a great capability. C is the concentration. A is the measured absorbance. I naught is the incident intensity. IT is the transmitted intensity. So these two are the most common, but there can be other types of detectors as well. One of the ones that's really useful is an electrospray ionization detector, and basically what happens is the material is the solvent is removed in a stream, and whatever material is left over scatters light, and based on the amount of light that's scattered, that tells you how much stuff is in the mixture. That's where we will end today. Thank you very much for your attention.